Hello, students, and welcome back. We are finally getting to a very, very important theorem. In fact, it's the fundamental theorem of calculus. And this theorem will allow us to calculate the area under the curve without doing the limits and the summation notation that took you a whole page. And it will also allow us to find the area under the curve for functions where you would not be able to do so using a geometric formula. So the fundamental theorem is used to evaluate a definite integral. And so you can see that we have the theorem stated here symbolically. The integral from a to b of f of x dx equals f. Now that capital F is the antiderivative, and then you'll plug in the upper limit of integration, so f of b minus, and then f of, and you'll plug in the lower limit of integration. So we will find the antiderivative as we have before, but there will not be a plus c. So no constant of integration. You should get a numerical value. And you'll see a notation that we'll use for evaluating is sometimes it's just a line, or I tend to use brackets. My number 4 in the steps, if you have absolute value as part of the function, you will need to first of all find the zero of that function. So in other words, find the vertex, and then you'll have a negative branch and a positive branch that you'll need to use as we integrate with absolute value. If you're asked to find area under the curve, that is nothing more than finding the integral. But if that shaded region is below the x-axis, then you use the negative of that integral. So we'll take a look at your first example. And for that, we have the integral from -2 to -1 of u minus 1 over u squared du. So we want to rewrite this so that we can do the power rule. So we'll have u minus u to the -2 du. And then we'll do the antiderivative. So for the u, that would be u squared over 2. I'm going to erase that and make that look a little bit better. And then for the second part of that, we'll have minus u to the -1 over -1. Now here's where you in the past have put plus c, but now you're going to plug in, or you're going to indicate that you'll be doing the fundamental theorem of calculus. And like I said, I use brackets. Sometimes you'll just see a line drawn, and you'll put the numbers, your lower and your upper limit of integration. Now, I like to usually take a step and simplify after doing the antiderivative. I also think when you're plugging in numbers, you do better if you avoid the negative exponents. So notice that a double negative, I made it positive. Then u to the -1 would be 1 over u. We're evaluating that from -2 to -1. So then next you're going to apply the fundamental theorem of calculus, which means you're going to substitute in your numbers. We substitute in the top one first. So it's f of b. So your b is the -1, your a is the -2. We'll substitute in -1 squared over 2 plus 1 over -1. and then it's minus, and you must use parentheses, negative 2 squared over 2 plus 1 over negative 2. Again, substituting in the b first and then the a into the antiderivative. Simplifying, we would get 1/2 minus 1 minus, and then we get 4 over 2. That would be a 2, and distribute your minus sign. So it's a negative of a negative 1/2. That would be a positive 1/2. Combining your like terms, 1/2 and 1/2 would be 1. 1 minus 1 is 0. Minus 2 would be your answer. So notice that we got a numerical answer for the definite integral. So there's the first example. I'd like to do an absolute value example, if you'll turn your papers over on example 2. Now, remember that in your instructions, we said that absolute value, you need to break up the integral. And that's because if you just integrate, I'll try to think of this from a graphing perspective. If you just integrate 2x minus 3, that's a line with a positive slope. But absolute values are V-shapes. So you have to take into account that you have another ray, actually, that is exactly the same as your 2x minus 3, except it is a negative slope. So we have your positive branch of 2x minus 3, and you have your negative branch of the negative of 2x minus 3. So what we'll do is find the vertex of this absolute value. And so we'll set 2x minus 3 equal to 0. And solving that, we get x equals 3/2. And that's going to let us then separate this. We'll go from, on our integral, 0 to the vertex x, 3/2. And this would be the negative branch of the absolute value. Now, you can either think of that graphically, or if you were to substitute a number between 0 and 3/2, such as 1, if you were to substitute 1 in for x, you would get 2 times 1 minus 3. You would get a negative and have to convert that to a positive. So in other words, using the opposite sign, that means you're on the negative branch of the absolute value. We're going to add to that, and we're going to continue on and go from the vertex 3/2 to where the integral originally was designated at 3. And this time we're using the positive branch. Again, if you wanted to think about another way to do this, you could put in a number between 3/2 and 3, like 2. If you plug that into your absolute value, you get 2 times 2 minus 3. That's a positive 1, no sign change. You're on the positive branch of the absolute value. So now we're, actually, I'm going to take one step and distribute that negative sign. So from 0 to 3/2, making that negative 2x plus 3 dx. And I'm just going to recopy this one, 3/2 to 3 of 2x minus 3 dx. Okay, so now we are ready to apply the power rule. So that would be negative 2x squared over 2 plus 3x. This is being evaluated from 0 to 3/2. And then your next one is, so we'll add on 2x squared over 2 minus 3x, evaluated from 3/2 up to 3. Again, you could take a line and simplify a little bit, so that would be negative x squared plus 3x, going from 0 to 3/2, and then x squared minus 3x, going from 3/2 up to 3. So now you're going to apply the the fundamental theorem of calculus by plugging in your numbers. Remember that it's f of b minus f of a, and we'll have to do this twice. So it is negative and then 3/2 squared plus 3 times 3/2. So there's f of b minus, and then f of a, we have negative 0 squared plus 3 times 0. 0 is always a great number to plug in, but if it's not 0, do be very careful about your positives and negatives. And so then I'm ready to do the second part of this. So plus, now I'll be working on substituting in. In fact, I think I'm going to put a bracket around this to maybe help you see the sections. So I'm ready to do f of b again, except my b this time is the 3. So 3 squared minus 3 times 3. And then remember it's f of b minus f of a, so minus, put a parentheses, and then the 3/2 would be squared minus 3 times 3/2. So then we're just ready to simplify all of this. So we'll have negative 9/4 plus, and then we have 9/2. That next section is just going to be minus 0. And then we're ready for, in the second bracket, we'll have 9 minus 9 minus, we'll be distributing our negative sign. The 3/2 squared would be 9/4, and distributing the negative sign, we'll have plus 9/2. And as we put things together, the 9 and the negative 9 cancels, but you do have the negative 9/4 and the negative 9/4. So that would be negative 18 over 4 plus, and then the 9/2 and the 9/2, which would be 18 over 2. If you get common denominators, then you'll have negative 18/4 plus 36/4, and that's going to end up being 18/4, which reduces to 9/2. So the area under the absolute value 2x minus 3 would be equal to 9/2 when you're evaluating it from 0 to 3. All right, I'd like to move on and do a trig problem with you. So just a little reminder about how those trig functions will work. There's no need to do any kind of a rewrite on this, so we can dive right into doing the antiderivative. So the antiderivative of 2 is 2x, And then the antiderivative of cosecant squared of x is actually negative cotangent of x. So we have minus negative cotangent of x. And then this is evaluated from pi over 4 to pi over 2. So I'll simplify it just a bit with the double negative, 2x plus cotangent of x. Again, from pi over 4 to pi over 2. And now I'm ready to apply the fundamental theorem of calculus. So I'll plug in my b, which is pi over 2, and then my a, pi over 4. So 2 times pi over 2 plus the cotangent of pi over 2, and then minus, now I'm ready to use my parentheses because I'm doing f of a now. So 2 times pi over 4, and then plus the cotangent of pi over 4. I'll use some parentheses there. And so 2 times pi over 2, that would give me pi, plus the cotangent of pi over 2. Pi over 2 is at your 90-degree angle. The cotangent would be the x over the y, and that's going to be 0. And then minus, we'll have 2 times pi over 4. That would be pi over 2. And then the minus sign will distribute, and the cotangent of pi over 4, well, your pi over 4 has the matching x and y, square root 2 over 2 over square root 2 over 2, which would be a 1. And so when you combine, you can get a common denominator with your pi being 2 pi over 2 minus the pi over 2. That's going to give you pi over 2 minus 1. And that would be the area under the curve from pi over 4 to pi over 2 for 2 minus the cosecant squared of x. And then our final example is really more about following instructions and understanding what those instructions mean. So your final example is asking you to find the area of the region. So this area word needs to be a key word to you that means I'm going to have to integrate. Your function is y equals 1 plus the third root of x. So right away, you can state that you're going to be integrating and finding area. 1 plus, now your third root, you should just go ahead and rewrite that as x to the 1/3 power dx. And then you want to look for your limits of integration, which are x's. So notice that you have from x equals 0 to x equals 8. Those are your limits of integration. And then this is usually thrown in, and that's just the x-axis. That's letting you know that this is bounded by the x-axis. So your area is going to be this integral from 0 to 8. That will give you under the curve and above the x-axis. So we've already taken care of the rewrite. We're ready actually to do the power rule. So that would be 1x plus, and then x, when we add 1 to 1/3, we get 4/3, and then it's divided by 4/3. And this is evaluated from 0 to 8. So simplifying just a little bit, 1x plus, and then our 4/3, we would multiply by the reciprocal 3/4 times x to the 4/3 power. And you may want to change your 4/3 power into a third root. Actually, I think I'm going to do that with you. So we'll change that into the third root of x to the 4th power. You might find that that's a little bit easier to deal with. So now we're ready to apply the fundamental theorem of calculus. So we'll plug in our b, which is 8, and then the a, which is 0. So the area will equal, all right, so 1 times 8, that's just 8, plus, and then it's 3/4 times, and it was the third root of our 8 to the 4th power. And I'm wondering if you know a quick way to evaluate that. So stick with me here. Minus, and then we'll do f of a, which is your 0. So we'll have 0 plus 3/4 times the third root of 0 to the 4th power. Write that a little bit better. So once again, the third root of 0 to the 4th power. Okay, so evaluating, we'll have 8, or a equals 8 plus 3/4. Now, in case you didn't know it, you can do either 8 to the 4th first and then do the third root, or you could do the third root of 8, which is much easier. The third root of 8 is 2, and then do 2 to the 4th power. And then you don't even need a calculator. So the third root of 8 is 2, and 2 to the 4th is 16. So you're taking 3/4 times 16. And then this last part is 0. And so we'll have 8 plus, and then 3/4 of 16 is 12. And so the area under the curve is 20. And so I hate to tell you this, but I've had you do a lot of work here. And you have to admit that this is better than doing the limit definition. But even better than that, your graphing calculators will actually evaluate area under a curve. And so I have those instructions for you at the bottom of your notes. Now this is using the TI 83 or 84. I also have instructions, but I do not have them on here. So contact me if you need to. I have instructions for how to do this on the Casio. And I will investigate if the Desmos program calculates area under the curve. But actually, the TI 83 and 84 is very easy to use. So you can practice those two methods. I can't get that part on the video, but there will be problems where I will allow you to use the calculator because it will do all the work for you. There will be plenty of problems, though, where I will want you to do the work as shown with the fundamental theorem of calculus on your notes. So good luck on your homework, and be sure to continue to ask questions.